So now we'll talk about off-diagonal elements of the strain rate tensor Sij. And the off-diagonal elements just represent the shear, not any elongation. And we'll consider the case in 2D. So we'll have our two axes here, 1 and 2, and we'll have the origin at some point x1, x2. And we'll consider two orthogonal fluid line elements of the length delta x2 and delta x1. And we will look at how they rotate towards each other under shear flow. And so the only flow that we'll consider is here this delta x1 element is advected by u2 at x1 and u2 at x1 plus delta x1 at the other end, which by Taylor expansion we can just write as u2 x1 plus delta x1 du2 dx1. And similarly here we'll act on delta x2 at the bottom end by u1 x2, and up here it's going to be u1 x2 plus delta x2, which is exactly, well, approximately u1 x2 plus delta x2 du1 dx2 by Taylor expansion. So this is the state of these two line elements at time t. Now they are advected and deformed, and at time t plus delta t they look slightly differently. So the origin of the two elements, if this was our original elements, delta x2 and delta x1, then the starting point will still be the same because it underwent the same u1, u2 displacement. But the new line elements are going to be moved, they're going to be rotated. And the top one, let's call that rotation angle delta d beta, and this here is d alpha. And so the displacement from here to here is just u1 dt, whereas the displacement from this location to this location here is u1 plus delta x2 du1 dx2 times dt. So the length of displacement here, delta L1, is just the difference between these two. And you will see that that difference is just delta x2 du1 dx2 times dt. And similarly, the displacement from down here all the way to up here is u2 dt. And for the other end of the line element, you go from down here to up here, and your displacement is u2 plus delta x1 du2 dx1 times dt. So the difference, delta L2, is delta x1 times du2 dx1 times dt. So we can calculate our angles using simple geometry, namely tan of d beta is approximately d beta by small angle approximation, and that is just 1 over delta x2 times delta x2 du1 dx2 dt, which is just du1 dx2 dt, since the delta x2 cancel. Similarly, d alpha is just du2 dx1 dt. So the average rate that the two perpendicular line elements rotate towards each other, let me write that out. The average rate of perpendicular line elements rotating towards each other is then just given by a half d by dt times alpha plus beta, which in the limit of small t, so when t goes to 0, this becomes a half 1 over dt d alpha plus d beta. And so if we now plug in 1 and 2 into these two expressions here for d alpha and d beta, you will find that this is simply a half du1 dx2 plus du2 dx1. And that, if you look back in your notes, is by definition just S1, and since the strain rate tensor is symmetric, it's the same as S21. And so this here is our measure of shear. So S12, the element S12 of our strain rate tensor, is essentially just how much shear does a fluid element undergo in a given unit of time.